November 121 Mike, taxi to runway 1.
Hi, I'm Mike Thompson, and welcome to 121 Point Mike. Today, we're going to work on our weight and balance. My weight is within normal limits, and my balance is quite good. So, let's work on yours. Weight and balance is one of the first pre-flight activities that you'll do. It's something that doesn't change, and so you can do it long before you take to the skies. Weather can change quickly, so a weather briefing can be done later. You can do weight and balance days ahead of your actual trip as long as you don't change the load. Weight and balance is all about balancing a plane along its length. But you may wonder why you need to do this at all. When you fly commercially, they don't do this. Well, actually, they do. They just do it behind the scenes. They use luggage and fuel to balance the plane. Weighing passengers would be bad for business. But I wish they would, because I'm way under the average weight they use to figure weights, and I'd fly pretty cheap. I don't enjoy subsidizing other people's tickets. So here's why weight and balance is so important. It keeps the plane from crashing. And that's good, right? I'm sure you remember from intro physics and geometry that objects behave as if all of their mass is concentrated in a single point. This point is called the center of gravity, or center of mass. A wing, or any body in motion, doesn't experience forces about its center of gravity, though. It experiences forces about a center of pressure, or in this case of a wing, we'll call it the center of lift. When a wing is flying, its center of lift is about here for most wings, and an airplane's whole center of gravity is typically in front of this point. So there's a safe range for exactly where the CG can be, and that's determined by the tail. You can see, though, that if you have a downward force here due to gravity and an upward force here due to lift, then you have a torque. And that tends to rotate the entire system this way. And so how do people stay in their seats and drinks remain on their trays? The tail. The tail is also an airfoil with its own center of lift, way the heck back here. We use the elevator to control the amount of lift that the tail creates. So in order to balance this system, the tail typically flies upside down. Yes, it's producing negative lift and pushing down. It has to, right, in order to balance our plane? So if we have a down force here and an up force here, then we have to have a down force back here. But it can be a smaller force because it's so far away. Remember, torque is force times distance, so if one goes up, the other goes down. The tail distance is large, and so the force can be smaller. But the tail can only push so hard, and that's why the CG can safely exist within a range. We need to do our weight and balance calculations before flight to ensure that we've loaded the plane properly within this range, and make adjustments if necessary. If the CG is too far forward, your nose is heavy and you may not be able to climb. If the CG is too far aft, then the plane will be unstable and you may not be able to recover from a stall. And that's why calculating your weight is so important. We would like to be able to end our flight at the time and place of our choosing, instead of letting the plane make that choice for us. So we also always do a thorough pre-flight inspection for the same reasons. But now that you understand why it's important to do weight and balance calculations, let's do a bunch of them so you can actually get comfortable doing it. It's really easy and there's no complex math involved at all. You'll see weight and balance problems on your test. So let's do a quick example with just the numbers only to get you familiar with finding the CG of a system. If we have 50 pounds at 30 inches, 10 pounds at minus 12 inches, and 90 pounds at 20 inches, we calculate all the moments and then add up all the masses, and then divide the two. So the moments are 50 times 30 for 1,500 inch pounds, 10 times minus 12 for minus 120, and 90 times 20 for 1,800 inch pounds. Now we add all those up, and we get 3,180 inch pounds. But why is the 120 negative? Because that weight is in front of the point that we're measuring from. As long as we're consistent, though, where we measure from, we're fine. The distances and moments will all be given in your airplane manual, so it's not like you have to get out there with a tape measure and measure all the distances on your own. And now we add up all the weights of 50, 10, and 90 to get 150 pounds. We divide 3180 by 150 to get 21.2 inches. And that's where the center of all this stuff is concentrated. See, I told you it wasn't that hard. Okay, well now let's use some realistic numbers. Try to do this along with me. and hit pause if you need more time to run the numbers on your own before I show you the answer.
So we have an airplane empty weight of 1397, and that's at 37.35 inches. We've got 35 gallons, now that's at 6 pounds per gallon, and the fuel's at 47.8. The front seaters are 340 pounds total at 37.1. The back seat passengers are 340 pounds as well. They're located at 72.9. And we've got 13 pounds of luggage at 92.3.
Now, our goal is to find out what the CG is and then determine if this was within the safe range. Here's a few things you notice in this example, though. You see that the weights of the people are 340 pounds front and back. Well, the FAA and commercial airlines assume that the average weight of a person is 170 pounds, which probably isn't true anymore. This airplane holds 4 people, and so for this example, we're just using the FAA average weight. You, of course, shouldn't do this for small planes because they are much more sensitive to differences in weights than the airliners are. You really must weigh everything you intend to put on the plane. Now, this is a sensitive topic for some, but if you explain that it's for flight safety, they'll probably understand. You can do it discreetly, or you can not take them. I would never take chances on overloading or improperly loading a plane, and you shouldn't either. So, to calculate a CG, we take the sum of all the moments and then divide by the sum of all the masses. A moment is a force times the distance, so let's do that.
And so the airplane at 1397 at 37.35 gives us a total moment of 52,178. Fuel at 6 pounds per gallon times 35 gallons is 210 at 47.8. Gets us 10,038. The front seaters, 340 at 37.1, is a moment of 12,614. The back passengers are 340 times 72.9, and that's 24,786. And the luggage way in the back at 92.3 is 1,200. And our total weight is 2,300 pounds.
2,300 also happens to be the maximum gross weight of our plane. We can't take any more weight safely. Now this is really important. I don't know of any small plane that will allow you to fill the tanks and the seats and take all your cargo. There's always a trade-off. You can either carry more stuff or more fuel. In order to take our average size passengers and one teeny tiny bag, we had to forego some fuel and a lot of luggage. If this is going to be a long trip, you're going to need to make a fuel stop and buy some stuff when you get there. On credit, though, because we can't afford the weight of any extra dollar bills. So we're on the weight limit, and that's okay. But where's our CG? This is the second piece of the puzzle. To find that, we divide all the moments, which are in inch pounds, by all the weights, which are in pounds, to get inches, which is what we want.
So it's 100,816 over 2,300, and that gets us 43.8 inches.
And at a weight of 2,300 pounds, the allowable CG range is 38.47 to 47.39. So we're okay. We're in the back half, but we're okay. From a stability standpoint, it's always safer to be front heavy than tail heavy, though. But how do you know what the range is for a particular weight and such? Or are you saying, I'm more of a visual learner? Well, guess what? Inside your flight manual, you're going to find performance section. It's going to include weight and balance. You'll see some charts that look like this, some tables maybe, charts that look like this. Let's show you how to actually use these things, shall we? Okay, so when you load a plane, right, you're going to have some stuff up here, say the pilot and the front passenger. Up in the wings here, you're going to have some fuel. That's got a weight. Here you'll have rear passengers. You may have some baggage back here. And you may have to account for some oil and stuff up here. And then of course you've got the plane. I'll make that a double arrow because it's the heaviest load. So all these things have to balance. Well, that's what calculating the weight and balance will allow you to do. So let me show you how you actually do that to figure out where in here your CG actually is. So they've got a sample worked out here for you. This one is a little bit different than, say, you might find in a Piper.
This one actually deals in moments. You don't calculate the moment. The graph will do that for you. Let me show you what I mean. So we're going to run through our weights and our moments here on this little table. Let me show you how to do this. The empty weight of the plane for this isn't going to change for the example. The empty weight is always going to be 1364, which means our moment's going to be 51.7. They've already done the oil for us because this chart doesn't have any way to do negative distances. Fuel, standard fuel. We always want to take off with full tanks, like I mentioned, so that's still going to be 228 pounds at 10.9. Okay, we don't have any long-range tanks. Pilot and front passenger. This is going to be a little different. So let's say in the front seat we've only got a 150-pound person. Okay, now we need to find his moment. We don't have the distances listed for us, so we're not going to calculate the moments. We're going to use this loading graph to find the moment. This is pretty simple. There's a different line for each of the positions on this plane. For the pilot and front passenger position, it's this line here. For the fuel, it's this line. And you see the further back you go, the shallower the line gets. Okay? And this line is going to do the math for you. So we're going to go up the front pilot and passenger line here, and when we intersect our load that we put at that spot of 150, we're going to come up, we're going to hit 150, and we're going to come down. We got to figure out what the scale is on this. There's a whole bunch of little hatch marks here. See? So these are in 0.5 increments. So that means our moment for this is 5.5, or 5,500 inch-pounds. But you can see here that this is in moments over 1,000. So we're just 5.5 to keep everything consistent. Okay, rear passengers. Let's put a little more load back there. Let's say we've got 300 pounds back there. Okay, so we'll do the similar thing. We'll pick the rear passengers line here, and we're going to go up the line like this until we intersect the 300-pound line, which is right there. Okay, when we get to there, we're going to come straight down and read our moment off the bottom of this graph here. So that would be 21, 20, right at 22. 22. And then baggage. You can put up to 120 pounds of baggage in the back. We don't need that much today. Let's put 60 pounds in. So we'll put 60 pounds of bags. So we'll take the baggage line. We'll go up till we hit 60, which is right there. These are in 10 increments. And drop straight down. And that gives us a 6. 6. So we're going to add up all these, and we're going to add up all these, and then we're going to divide the two. 2117. Okay, we're going to add up our moments. 51.7 plus -2, because everything is measured, in our case, probably from the firewall. And so this is a negative number because it's a negative distance. Negative x is forward of your datum, positive x is all aft of your datum. So that's why that's negative. So I get 95.9 FM. Okay. And so we can now use this to find out where our CG is located. I mean, we can divide this, of course, real quick. Let me show you here. This is in inch-pounds over 1,000, so it's 95,900. So if we take this, 95,900, divided by our total weight, 2117, that's going to get us 45.3 inches. So we're going to go here. We're going to go to our weight line, 2117. So we're going to call it 2120. So we're on this line here. We're going to come across, and I'm just going to draw a whole line all the way across. Okay? And now we find our moment that was at the bottom, 95.9. 95.9. We're going to call that 96. So we're going to get 96 and come up. Right there. So we are okay. And we know our CG is actually at 45.3. But it's really irrelevant because on this graph here, it's just showing us here's our moments, here's our weights. Where these two intersect, is it within this zone? We are in the normal category, so no limited aerobatics or anything. We have to fly like normal people today, the whole way. But we are okay because we are in this zone. Hopefully that makes sense. Let's do another one. Okay, for our second example here, we'll do this one more time so you can get used to doing it. The empty weight of our plane's not going to change. So that's still 1364. And of course our moment's not going to change. We're still going to use full oil. Fuel, our tanks aren't quite full this time. I checked and it looks like we've only got about 20 gallons or so, but this is a short flight, so we're going to be okay. So to calculate this one, we're going to go up this line here, the fuel line. We're going to go up to the 20-gallon mark, and we're going to drop it down. It looks to be just less than 6. We'll call that 5.75. Well, to the nearest tenth is okay. 120 pounds. And I said that that was at, we're going to call that 5.7. Okay. Long-range tanks, obviously. We can't be using the long-range tanks. We don't have our regular tanks full. So now for the pilot and front passenger, this one's a little bit different because this line is, these are all calculated for the average. You notice here it says station 34 to 46. Well, that's because the front seats are adjustable, and where you place them will of course affect your weight and balance. Let me show you here. Back in the performance section of the manual, you can see here it says loading arrangements. Pilot and front passenger, 34 to 46. And so this here is not really useful if you're going to use anything other than 37, right? So you've still got 3 notches ahead, and you got, 9 notches behind this average 37, where this graph is calculated from. And so if your seats are all the way back because you're really tall, or if they're all the way forward because you're really short, you really can't use this line to calculate your front moment with a lot of accuracy. So let's do this. Let's say that our seats are all the way forward. And of course, the seats operate independently, don't they? So you may have to average those out. But I just wanted to let you know that this for the pilot and front passenger with adjustable seats doesn't always apply. So let's calculate it with 34, right? So let's say we've got 250-pound people, so we've got 300 pounds up front, but it's at 34, right? We're going to do that at 34. So we can't use this loading graph, but this is easy to do, right? A moment is a force times the distance. Let's clear that. 300 times 34 is 10,200. But remember, all these numbers are to the thousandth, so it's just 10.2. Makes it a lot easier. We don't have to write down a bunch of zeros. Okay, rear passengers, those seats don't move, so we're okay there. Let's say that we don't have anybody going there, but we are taking a whole bunch of baggage. So we're going to max that sucker out at 120, and it's the same as it was last time, but I don't remember what it was necessarily, 11.5. Okay, so same as before. We're going to total up all of our weights and all of our moments. 1919, okay. 78.9. And so now to find our CG, remember it's the sum of the moments over the sum of the masses. But remember this moment has been divided by 1,000, so it's 78,900 divided by 1919, which is 41.1 inches. Okay? So we don't need this one anymore. We're going to go on to this chart. So we're going to locate our moment and our weight. And so our weight is here on this line, 1920. And our moment of 78.9 is basically 80 or 79. These are in 1, 2, 3. These are in ones. So we're going to call that 79. So we are right here. Excellent. Pretty much right smack dab in the middle of everything. Okay, this loading will work. Now, a lot of the times when you're doing your weight and balance, you're not going to see a chart that looks like this with moments across the bottom. You're going to see a chart more like this or like this that has the CG location across the bottom. It's just a different way to present it. And this is probably more common with the CG. And if you do it that way, it's really simple. So let me show you here how we do that. You already know how to do that, right? It's the sum of the moments over the sum of the weights. In our case, for this problem, the moment is 94, but it's times 1,000. So we're 94,000 divided by our weight, which is 2,080 pounds. I'll write that. So it's 94,000 over 2,080 pounds. 2080. 45.19. Now, if we go over to one for a Piper Archer, the PA 28181, you'll see here that we can't just, it's a different airplane, and we can't just translate it. These numbers are much, much bigger. Look, 45 is not even on our chart. Well, you may wonder, why is that? Why isn't that on it? Well, because they're simply measuring from a different spot. Of course, in pretty much all planes, the CG, is going to be somewhere here within the wings. Well, in the Cessna's case, they're measuring from somewhere around here. But for this Piper chart here, they're measuring out in here. Or maybe they may be measuring right there. I'm not sure where they're measuring for this particular plane, but they're measuring much farther forward. And obviously, if you're measuring from a distance farther forward, your CG number here, is going to be much larger because it's a bigger distance. And so that's how you would do that. But similarly, once you find your CG, let's just say it's 90 in this case. We'll double that number just for examples. You'll go up, to your 90 wherever. And we can still use our same weight of 2080. This is 2,000, 2,100. So 2080 would be right about there. So for this Piper Archer, we'd be right there. This one here is for a PA 34200. This is a twin engine. But it's the same thing. You find your CG first, down here, and then your weights up here, and you intersect. This one here has a slight fan shape to it, but you run it the exact same way. We can do it as well. So we'll just pretend that 90 is our line here, and let's say for our loading purposes, maybe we loaded at 3,500 pounds. We would interpolate here, come across, and we'd be right there. So even though the charts for this look different and they're not done in moments, it's the exact same procedure. You just need to add the one extra step of actually finding your CG by dividing your moments by your weights. Okay, let's do a scenario here that you might see on a test. Let's say the plane weighs 3,000 pounds and its CG is at 69 inches. So, where is the CG going to be after 90 minutes of flight? The fuel station is at 64, and you burn 9 gallons per hour. Okay? You may wonder how in the world you're going to find this. Well, I'm going to show you the simple math way to do this, rather than just guessing and checking answers on your test. So, let's calculate our total moment, right? So, moment right now is 3,000 times 69. 3,000 times 69 is 207K. All right. Now, we know that we're burning 9 gallons an hour. We know where the fuel is located, so we can calculate the weight of this, right? The weight of this fuel is 9 times 6, isn't it? Which is 54. That's 54 pounds. But it's 90 minutes, okay? So it's going to be 50% more than it, because that's an hour and a half. 54 times 1.5. Our total burn is 81 pounds. So, that looks like 9.6. I should use the X. And we know that this is at 64, isn't it? So the moment created by the fuel is this. It's 81 times 64. We're going to, a delta moment, it's not a sum of the moments this time. It's a delta moment, 5,184. Okay, so our moment is going to drop by this much. So we take 207, I'm going to add the zeros now, since we're going to need them, minus 5,184, 201, 816. That's our new moment. New weight equals 3,000 minus our burn, right, which is 2,919. So our new CG is equal to the sum of our new moment, 201, 816, divided by 2919, 69.1, we'll call it 14. And there's your answer. That's where the new CG is after an hour and a half of flight. Notice it was here, now it's here. Didn't move very much, did it? Just over 1/8 of an inch. And of course it didn't move much, because airplane designers are smart people, and they put the fuel near the CG of the plane. Because as you burn fuel or add fuel, you certainly don't want your CG, hopping all over the place. You want it to stay pretty well the same, because the fuel load is going to change drastically in flight. And so those brilliant designers locate the fuel near the CG. And the wings are a great spot for that. Okay, I showed you how to do it here with the math. Let me show you how to do this exact same problem in the computer. You're going to go to the weight and balance. You're going to go weight and arm, since that's what we're given. We're given CG locations rather than moments like you'd use on the Cessna's graph. So weight and arm, enter. Our weight is 3,000, enter. The CG of our plane is 69, enter. Reference factor is 1 because we're dealing in pounds, we're not dividing anything. It gives us our moment of 207. We're going to hit enter to cycle back to the weight line. We can do math here, let me show you. So we're going to burn 9 gallons times 1.5, so we're 9 times 1.5 equals 13.5 times 6. 81. Look at that. We didn't have to actually do any math on our own. You can do math on the lines. Just make sure you hit equals, not enter. Once you get the thing you want on that line, we're actually going to have minus 81, aren't we? Because we're burning that fuel. So I'm going to hit the negative key. I've got negative 81. Now I can enter. The fuel was located at station 64. Enter. You can see that. Our gross weight dropped. And there we go. That's the answer. Nothing else to do. Our CG is flashing at us at 69.14. Look at that. That's exactly where we calculated it to be. So that's how you can do it in the computer. And of course, now if you want to add more fuel when you get to your fuel stop, let's say you weren't full to begin with and you want to take on some fuel, we'll cycle back to weight. Let's add an additional, so let's add arbitrary gallons. So we'll go 12 gallons times 6. Because we're not doing time this time, so we don't need the 1.5. So we're going to add 72 pounds at the same arm, right? That saved the arm as before. So we're going to hit enter. And there, our weight went up, our CG recomputed. Simple as that. Okay, let's do one more common scenario that you might see. Let's say you've got back here at station 160, and up here, let's say this is the front seat, maybe is station 40. How much weight do you need to move from here to here in order to move the CG from 90 to 88 and bring it within limits? Okay? So here's our problem scenario. Okay? It's not a hard problem. So once again, we're going to calculate our current moment. We're going to call that moment now is 3550 times 90, 319,500. Okay. The overall total weight's not going to change, is it? We're just going to move some weight around. So that's maybe the big nugget here in this, is the weight doesn't change. But we know where our new CG is going to be. So we're going to compute that moment. 3550 times 88 is 312, 400. Okay, this was our old moment. Here's our new moment. Is 7,100. The delta moment is 7,100. My head agrees. All we can do, right, we know what the distance is. We know what our moment change is going to be. So we're simply going to divide the moment change by the change in our distance to get the amount of weight we need to move. Okay, I'm going to do this one over here. So we're going to take 7,100 divided by 120, which equals 59.2 pounds. We need to move at least this much weight in order to get our CG within limits so that we can fly safely. So you see, that wasn't that difficult. The weight didn't change. We calculated the old moment with the old CG, the new moment, and you would pull this number maybe off a graph in the real world, right? So if you say your CG, you know, this chart doesn't work, but let's say your CG was here, right? You need to move it to here. You would come down and see, here's your new, right? And there's your old. There's your new and old moments. So you could calculate that. So if you were loaded out here, you would know what your moment needed to change by on this case. Or of course, if you're using one of the other graphs, if you were like this and you were loaded here, you needed to move to here, right? There's your old CG, and there would be your new CG. And you know if you make that change, you're within limits. So that's the practical application for all this math right here.
I really enjoy doing weight and balance problems, and with a bit of practice, you're going to get quite good at it. So go back to some of those diagrams I showed you and maybe create some loading scenarios to practice with. I've shown you the scenarios that you will encounter in real life and on an FAA knowledge test. Practice a few on your own, and you can email me with any questions, or you can connect with me on PalTap. It's this cool new video chat service that allows you to get quick answers and discuss more complex issues much faster than a long back and forth email chain. The link to my PalTap profile is in the video description. Now that you're familiar with how to do weight and balance, you know how to safely load a plane and pass the questions on your FAA knowledge test. Click the subscription button so that you can be notified when the next video is out. And stay with me on 121 Mike.